Welcome back all of you for the UGC lecture series on laser applications and the Swayam portal. We are explaining about applications of laser. Out of that, we have come down to most important material processing applications or active applications. Before you start with the material, you need to prepare the laser for certain specific purpose. It is something like when you want to take a movie, you prepare the hero in certain fashion, the hero in certain fashion, comedian in certain dress and certain way. In a similar fashion, you have to prepare the laser in a way that you want, so that the final result will be very effective. That is what. Out of that, we have already seen one, that is the frequency conversion. That is, if you start with a laser of 600 nanometer, put a second harmonic generator, you should be able to get a laser at 300 nanometer, because for my particular application I need a laser only at 300 nanometer, not the laser at 600 nanometer. That is the reason I went on to second harmonic generation. I can give another very good example. The neodymium laser at 1064 nanometer will not be able to produce laser action from the dye solutions. On the other hand, if I put a second harmonic generator in between, the 1064 will be converted into 532, that is capable of pumping a large number, 50 to 60% of the dyes available in the market. So, I can get a laser from there, from the dye laser, which can be from 600, 610, 620, whatever wavelength I want. I can get a ray, you can get a range of lasers from dye solutions. On the other hand, if I get a third harmonic generator, insert it inside, I would be able to get a 355 nanometer, which is ultraviolet, with which I can pump any kind of dye solution, and I can produce laser from 400 nanometer to 800 nanometer at a stretch. At any wavelength you want, I can do, with some modification here and there. Because of this kind of requirement, we use second harmonic generation or third harmonic generation. Now, look at this one. We have been able to double the frequency or triple the frequency. Is there any other way that you can get somewhere in between 1.5 times or 1.3 times increase or decrease in the frequency? Yes, that is possible with certain other types of crystals. Let me go back to that. Start with the same laser. For simplicity, I would say the laser that I am using, fundamental laser, is 500 nanometer. That laser 500 nanometer is the wavelength will be 500 nanometer, wave number would be 20,000 centimeter inverse. This is important, this you should remember. Converting to that one, you will get 20,000 centimeter inverse. Next thing, suppose I put a crystal, for example, lithium niobate crystal on the way and adjust certain parameters of the angle or the tilt. There are so many by playing around, temperature, anything you can do. If you do all this one, the incident laser at 20,000 centimeter inverse will come out as 21,000 centimeter inverse and 19,000 centimeter inverse. That is 1000 centimeter inverse, an energy, a particular small component of the incident laser has been eaten up, so that 20,000 has become 19,000. This is called frequency down conversion. If the frequency has enhanced by 1000 centimeter inverse, then you say it is called frequency up conversion. This kind of additional or subtracting capability is called the parametric crystals. This kind of new frequency generation is called a parametric generation, because it depends on the crystalline parameters such as the angle of incidence, axis, temperature, capability of the particular crystal, what kind of group it contains. Is it I mean, it's a crystal, it has certain way of classification. What kind of crystal is that one? What kind of nonlinear property it has? All these are very complex property. These are all have been studied theoretically and experimentally. Nowadays, you can get a parametric generator available, ready made. You need to buy, insert it, get it. So, you can get, you start with the 20,000 centimeter inverse laser, you can get 121 or 19, 22, 23. It is like converting it, I mean buy it and cook it the way you like. This such a facilities have come up these days. Among these, there is something very, very interesting which I must now bring to your attention. This is called stimulator Raman scattering. Maybe you all must have studied, you are all graduate students, must have studied about Raman effect. Raman effect is just a scattering. Scattering means you take an object, most common scattering object that we are all very familiar is water. Allow the light to fall on water, then light will be scattered. When the light gets scattered, if the power of the laser light is really good, there will be a coupling between the incident laser and the frequency, vibrational frequency and the rotational frequency of water, so that what comes out will be a wavelength shifted Raman spectrum. Again, I go back to the next example. Suppose the vibrational mode of water, instead of water I would say benzene. The reason is the mercury vapor lamp falling on the benzene in a very crude experimental setup, which would cost not more than 50,000 rupees now, was the instrument which brought Nobel Prize for the first non-Asian Tamil scientist. This is something fantastic, because he used a mercury vapor lamp. He used 365 nanometer, he used to filter everything. I do not want to go to the very old story of Raman effect. He used the light, then he allowed this to fall on benzene. Benzene, you know the structure of benzene is very well known. It has many vibrational mode, and one of the vibrational mode of benzene was able to couple, connect up with the incident light. Then on the out, when it came out, what it came out as a scattered light is, Raman was able to see a discrete light at two different wavelengths. At one wavelength, it was shifted by 3000 centimeter minus. That means the instant light, take for example, if it is a 20,000 wave number light, 500 nanometer light, put a benzene, the vibrational frequency of benzene is, let us say, 3000 wave number. What Raman got is, eventually he got a light at 2700 centimeter inverse. There was a discrete difference in the output light. The scattering was not continuous. There was one light which was incident light at 20,000 wave number, and there was another which is 17,000 wave number. 3,000 wave number is less. Now, that shows the molecular energy level also is quantized, something very much similar to atomic energy level. I am talking about Raman effect with a very simple instrumentation which would not cost more than 50,000 rupees even at this level, at today's prize, he was able to demonstrate that the molecular energy level, the vibrational mode of molecule also is quantized as much as the electronic energy level of atoms are quantized. This was something a very great success for quantum mechanics. That was the reason why he got Nobel Prize. What was very important for us now is, after this particular discovery of Raman effect, many people did many experiments and they were able to show Raman effect is exhibited in many types of liquids, chlorine, chloroform or water or many things. And after that, within few years, there were so many research papers on Raman effect. After some time, it died down. There was not much of interest in Raman effect because experimentally it was very difficult. You need to have a high power laser with a very good resolution instrument, etc. And people have quietly forgot. Then what happened? When laser came in, since laser puts a large number of photons, when you switch on a laser, the light, the photon that come out from any laser is very, very high, plenty of photon. That is what is called the high bright light source. The brightness of the light is very, very high in the laser. That is, you will be able to get enormous number of photons from a small aperture. That is all it means for all application point of view. Such laser started reviving, rejuvenating, giving a new life to Raman effect. That is one step. And then again people started doing a lot of research in this one. That kind of spectroscopy is called laser Raman spectroscopy. Next step. After this, after some time, somebody used a high power laser like a ruby laser or a neodymium laser, particularly pulse laser. Then what happened is, they focused the laser, say neodymium laser of 1064 nanometer, they focus the light on the same benzene. The benzene is a favorite liquid for Raman. They use the same benzene, put a proper density, put a proper density means proper power density of laser on a long tube of benzene, ordinary benzene, which is commonly available, even your petrol is very good. Then they found a number of laser coming out from the petrol. Remember, this was something, a big surprise for Raman. Unfortunately, he was not alive to see the Raman laser. I want to differentiate. Laser Raman effect is something different from Raman laser observation. In laser Raman effect, what we did was just you start with the laser, often neodymium, often a helium laser or argon laser. These are the common lasers available. Put a material like a benzene, chloroform, water or any solid or even a gas, you put it, then what comes out will be the instant light, and then there will be another Raman lights, that is called Stokes shift and anti-Stokes. So, Stokes shift means you will have another line with lesser frequency. Anti-Stokes means you will have another line weaker than all the rest, that will be anti-Stokes line. These are common. This was the story for 10 or 15 years. Then when high power laser, Q switched or a mode locked laser came in a small short duration, enormous amount of energy was delivered, and then it produced a laser from the benzene, and that is called Raman laser. This is a Raman laser from benzene. What is beauty is, suppose I start with 532 of second harmonic of neodymium laser, put just small trough containing benzene, just to focus it, use a ordinary lens. What comes out will be 5 colors. You will get a green, you will get a blue, you will get a violet on one side. These are our anti-Stokes line. Not only that, I started with the green laser. I will be getting green, orange, red, pink. You will see a rainbow laser. You will see so many lasers coming out in the room. In my lab, I used to give a demo. You just start with this one, close the light, you will see a rainbow laser, very bright one, unbelievably beautiful, filling up the whole room. That kind of lasers are called stimulator. That comes due to the phenomenon called stimulator Raman scattering. For simplicity, we say it's a Raman laser. Now, these kind of laser also are used for variety of applications. Now, we have prepared, this is the example for Raman laser schematic. Now, what we have done so far is we have prepared the laser, changing its time duration, changing its pulse duration, changing its wavelength. That means it is something like a shooting. You have prepared everything. Actors, shooting cameraman, everybody is ready. Now we are going to the applications, particularly material processing applications. Only when all these arrangements are made, you can get a good applications. Now let us focus on what happens in laser material processing. The schematic is given. When you have a laser, this is really how it happens. Laser beam from somewhere it will come here, put a reflector, come down. The laser beam will come down as a light. Then put a lens so that it will be a very focused one. If such a laser is focused on this kind of wooden table, and if it is a CO2 laser, carbon dioxide laser, you can see big smoke, and this table will be cut into two, or it will drill a hole from this one within a minute. If you start ABCD, by the time there will be a hole driven in this one. Not only in the wooden table, if it is a thick aluminum, it will drill a hole within 10 seconds it can do. Such high power lasers are there. Why and how it works? There is a lot of theory on this one. I shall be just going into the essential feature of this one. In this particular graph, I have given the temperature as a function of depth of the material from the surface. 0 means on the top surface. 500 micron, see the bottom curve, 500 micron means 0.5 millimeter, that is from the bottom, from the top to half millimeter down. That is all what we are going to look at it. If I shine the laser on this one, the temperature, what will be the temperature? You will see the temperature from 0, it goes to very high temperature of about 1000 degree or even more, up to about, let us say, 50 micron. That means the whole process of very high temperature is localized on the first few layers of the sample. Then after 50 or 100 micron, that is after 0.1 millimeter, the temperature falls off very rapidly. That means we are able to produce a high temperature on the surface, leaving other part undamaged. This is a very, very great importance for surface hardening of material. I give an example, you will immediately smile at me. You know, people like me, we do the shaving every day. We use a blade. After 10 shaves, the blade gets rusted or it loses its sharpness. Now, if you take such a material and treat it with a laser, this kind of surface heating and cooling, this kind of very localized heating on the top surface will produce certain change in the crystalline structure of the alloy. They can be heated very specifically on the surface. We do not bother about the inner surface because we are going to do the shaving. For shaving, the top surface should be sharp and rust free. This is one aspect. Look at the other graph also on the top. Now, suppose we use a pulse laser, then in the top graph I have given the temperature as a function of time. Look at the time duration 0 to 2, that is what happens time of 2 microseconds. That is all what I am interested, because I am going to use a laser pulse of the order of 1 microsecond or 10 nanosecond. There are so many pulse laser, I can choose any one of them. What I am interested is what is the rate of change of temperature, how fast the temperature increases, how fast the temperature cools off. In this graph it clearly shows at a depth of 5 micron almost on the surface, the rate change of temperature is 10 power 6 per second. That means in a time duration of this, that is 1 second, remember this is 1 second. In a time duration of 1 second, the temperature goes from 30 degree to 1 million degree and then comes down. That is the meaning of this dou T divided by dou T. Top T represents the temperature, bottom one represents the time. The rate of change of temperature is about 10 power 6 per second. This is rapid heating and rapid cooling. When there is a rapid heating and rapid cooling, the hardness of the specimen will increase 10 times. You cannot drive a screwdriver, you cannot make a hole, it becomes so hot. This is called the surface hardness of variety of material which are used these days very commonly in all industries. Next question, what is the advantage of improving the hardness so high? When the hardness is so high, it becomes rust free. All of you know, most of the irons, wherever iron tools, many of them, they easily get rusted off. Suppose we are using this kind of iron or steel somewhere in an intricate material, intricate instrument, and it is a precise material, precision material, then you cannot remove it and put it back. It will be a disaster. So what we do, keep the component there, send a laser beam through an optical fiber. The optical fiber can reach in any part of the machine, and then whichever needs to be hardened and made rust free, you can use it and access this one. So this is one of the subtle part of rust free surface hardened material. This is one of the applications. There are many other applications. Another very interesting application is laser welding. Laser welding is another very big industry throughout the world. It has revolutionized industrial applications. For example, there are so many materials which cannot be welded. Iron and aluminum cannot be welded because they are not compatible. You can mix iron with zinc or certain other material, I am not sure about it. You cannot mix in one material with another, there should be lattice compatibility. Now, with this kind of heating, bringing two incompatible material coming together, making them welded is possible, and such kind of laser welding also has been very successful. Now, welding becomes, when you make two material coming together, it becomes welding. When you have a big material, if you want to cut into two, increase the energy of the laser beam, focus it very precisely, you can just draw a line across an aluminum or steel and it will make a precision cutting. Why should you do all this one? I can give an example. You must have seen, for a military, they must prepare a uniform for 1 million people, because military has so many people. So, what they will do, they will have only 3 sizes: small, medium, large. They would give order to CO2 laser for small, this is the size, give all the cloth, just a cloth, cut it in this fashion, all of them within a minute you can have a pack of cloth of so much thickness and switch on the laser. It will just very sharp, it is like a big knife, it will just cut it in two without any damage anywhere else. Such a precision cutting in a bulk is possible only with such a high power laser. This is for cutting. I told you about welding, I have told you about surface hardening. There are many other applications. Another very interesting application is a hole drilling. Hole drilling in a diamond is being done now at this time. At this time, you can, if you can straight go to Indore in Gujarat, you will see a technician who may not have an education beyond an SSLC. I have seen it, I have visited, I have seen whatever I am saying. He has got only some knowledge that here is a laser. All that he uses it, he knows how to use the laser. He takes a precaution that the laser beam does not hurt him. This is used for removing the dot or birthmark in the very expensive diamond. This might surprise you. Look, let me repeat. He is capable of removing the birthmark inside the diamond. We all know diamond is very precise, very expensive. A 1 carat diamond, very good diamond, would cost few lakhs of rupees, I do not know, few lakhs of rupees. Now, next step, suppose when the diamond is taken from some place, maybe South Africa for example, some of the diamond will be pure, very clear, transparent. Some of them will have certain flaw inside, some dark spot inside. That is something called natural inherited quality of that kind of diamond. I would not say inherited, that is a born, I mean birth defect of that particular type of diamond. How to remove it? Can we discard this one? No. They have found out very good, very smart idea. 1 carat of that very good quality diamond would cost, let us say, about 1 lakh of rupee. But this particular diamond has a birthmark. Then what do you do? Take it to Indore. They will use the same neodymium mag laser, fundamental, pulse laser. Focus to the inside of this one. Carefully focus to the inside of it. Switch on the laser. One pulse will just go burn it. Another pulse will go just burn it. Just keep on burning here and there, so that the dark spot will become a mild cloud, because it has been spread out. It is like just mixing your omelette. You just keep on stirring it, then it loses hardness, it will be spread out. So, you make a mild cloud, then take it out. That small change in the local mild cloud will not be visible for most of the purpose. Only for an expert, that kind of precision repairing has been done. Because of this one, they would sell the same kind of 1 carat diamond. Instead of 1 lakh, they will sell it as an offer for 50,000. 50,000 means that particular industry which repaired this diamond gets enormous profit of 50,000. And how much time? Actual time would take only for half an hour. Now, all these are not fictional stories which are being done. Such a very precision operation can be done using this kind of laser. Next one, which is very important, is microelectronics has been got profited enormously. That means a totally different lecture. I would elaborate it later, the importance of laser in microelectronics, particularly for chip making. because of the chip only you are able to get in your mobile all the audio or the video, or you can see your friend in USA from here. That comes by chip, and that is where laser has also played an important role. Thank you very much.